The University of Tokyo recently announced a device that claims to boost computer processing speed by 1,000 times while generating no heat. This headline has sparked excitement, but the reality is far more complex than the headlines suggest. The true stakes involve whether we are witnessing a fundamental shift in how we compute or merely a theoretical curiosity trapped in a lab. By the end of this explanation, you will understand the specific thermodynamic trade-offs that make this claim possible in theory but nearly impossible in practice. To understand the claim, we must first look at the physics of information. Every time a computer bit flips from 0 to 1, it erases information. According to the Landauer bound, this erasure must dissipate a minimum amount of energy as heat. Traditional silicon chips operate far above this limit, wasting massive amounts of energy just to reset their state. The University of Tokyo device appears to operate on the principle of adiabatic computing. This means it attempts to recover the energy used during a state transition rather than burning it off as waste heat. In a perfect adiabatic system, the energy is recycled, theoretically allowing for zero heat generation during operation. However, there is a critical catch that the headlines ignore. Achieving this energy recovery requires a specific type of switching speed. The system cannot simply snap between states like a light switch. It must transition slowly and smoothly to ensure no energy is lost to friction or resistance. This creates a fundamental trade-off. To approach the theoretical limit of zero heat, you must sacrifice speed. The very mechanism that prevents heat generation also throttles the clock frequency. This is why the claim of 1,000 times faster speed while generating no heat is so problematic. The physics suggests that if you get the heat down to near zero, you likely get the speed down as well. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The research indicates that current studies on adiabatic logic show a different reality. When researchers achieve near-zero heat dissipation, they often observe a temporary temperature doubling within the device itself. The energy is not disappearing, it is being stored temporarily in the system's internal states before being released. This leads to a situation where the device gets hotter, not cooler, during the transition period. The claim of simultaneous high speed and zero heat relies on a specific operational mode that has not been demonstrated at scale. It is a theoretical possibility, but the engineering reality involves managing these thermal spikes. Another layer of complexity lies in the materials science required to make this work. The device likely relies on superconducting materials or exotic states of matter that allow for reversible switching. These materials require extreme precision. To build a processor with billions of transistors, you need nanometer-scale uniformity across the entire chip. If even a small fraction of the transistors fail to switch reversibly, the energy recovery mechanism breaks down. The system reverts to standard dissipative behavior and the heat returns. Current manufacturing processes cannot guarantee the homogeneity required for billions of such transistors on a single die. This material homogeneity problem is a massive barrier to mass production that remains unsolved. We must also consider the architecture of the computation itself. The claim of 1,000 times speed increase likely stems from hyperdimensional computing architectures rather than raw processing power. In this approach, computers trade high-precision floating-point arithmetic for massive parallelism in binary vector spaces. This creates a massive performance gap only on specific artificial intelligence workloads. For general-purpose tasks like running an operating system or editing a video, the speed gain would not exist. The metric of 1,000 times faster is dependent on the specific task latency, not the raw throughput of the processor. It is a specialized tool, not a universal replacement for silicon. Even if we solve the material and architectural challenges, we face the interconnect bottleneck. A device that operates without heat generation does not mean the entire system operates without heat. The cryogenic cooling infrastructure required to maintain superconducting states introduces significant thermal loads. The signal routing for millions of interconnects between the processor and the rest of the system creates resistance and latency. These factors negate the theoretical gains in a rack-scale deployment. The thermal management of the device itself is solved, but the thermal management of the surrounding infrastructure remains a formidable engineering hurdle. This brings us to the most valuable insight regarding the future of computing. The shift is not just about faster chips or cooler data centers. It is a fundamental change in how we measure performance. For decades, the industry has optimized for floating point operations per second, or flops. This metric assumes that speed is the only thing that matters. As we approach the thermodynamic limits of silicon, we must shift our focus to energy per operation. Future system architects will prioritize algorithmic choices that fit reversible computing models over traditional von Neumann architectures. The value of a computation will be judged by how efficiently it uses energy, not just how fast it finishes. The distinction between a lab prototype and commercial viability remains a significant gap. The research highlights that, while thermodynamic computing offers a path to bypass silicon's thermal bottlenecks, the engineering challenges of scaling underdamped systems are formidable. The current evidence supports the potential for heat reduction, but it does not confirm the simultaneous realization of extreme speed gains or the absence of manufacturing barriers. We are looking at a theoretical possibility that has not yet been proven as an engineering reality. For data engineering careers, this signals a major pivot. The skills of optimizing for raw speed will become less valuable than the ability to design systems that minimize energy consumption. The transition from optimizing for flops to optimizing for energy per operation will define the next generation of computing infrastructure. This is not a story of a magic chip that solves everything. It is a story of a new paradigm that requires us to rethink the very foundations of how we process information. The road ahead is long and the physics are unforgiving, but the potential reward is a computing world that finally respects the laws of thermodynamics. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.